Testing. Okay, good evening. So I guess this is where we stopped last time. So we were talking about this digital communication system, where we define the two performance metrics. One is bit rate, the other is error probability. These are the two metrics, independent metrics that define the performance. And then we also define the resource metrics, right? For resource metric with respect to radio channel, we'll have the bandwidth and power, okay? So, and then we talk about there are four potential trade-offs between resources and performance. When you increase bandwidth, you can bring about an increase in bit rate, or you can also bring about a reduction in error probability. These two take different trade-off mechanism. Likewise, if you increase the power, the transmission power, you can bring about a reduction in error probability, or you can bring about an increase in bit rate. Again, these are two different mechanisms. So altogether, there are four different trade-off mechanisms. So we're going to, again, talk about this digital communication system, and so as to understand these four trade-off mechanisms. All right? And to illustrate the idea, we will focus on a very simple channel called additive white Gaussian noise channel. That is your received signal at the input of the receiver is the transmitted signal plus the noise, okay? So that's the only thing introduced by the channel. Just add noise to contaminate whatever you transmit, okay? So we'll look at the transmitter design first, digital modulator. So once again, I always like to start with a black box approach. So let's consider a binary modulator as a black box, okay? So a binary modulator would be like a black box has an input and output. The input is take one bit at one time. There's an input bit. And the output of the binary modulator would transmit a symbol. So this symbol, a waveform, would match the requirement of a channel. So if we are talking about a coaxial cable channel, then it will be a baseband signal. If we are talking about radio channel, then it would be a bandpass signal. Is that okay? So this signal is designed to match the requirement of channels. All right, so now there are two parameters that can fully define this black box. The first one is a symbol duration. Okay, how long is one symbol? The other important parameter is what I mean by a signal set, which consists of two signals or two symbols. Okay? So just two different waveforms will do the job. And then you put a label behind each symbol. So let's say this is for 1, this is for 0. So that means the operation of this binary modulator would be very straightforward. Every symbol duration, you take a look at the input bit. If the input bit is 1, your output symbol will be S1T. If your input bit is 0, your output symbol will be S2T. Is that okay? So S1T if the input bit is 1, S2T otherwise. Is that okay? Then you are done with the current symbol. And then you move on to the next symbol and repeat this bit by bit or symbol by symbol. Is that okay? So therefore, any one of us can dream up your own binary modulator. You just need to define two different symbols in the signal set. And then that will do the job as a binary modulator. Is that okay? So here we have two examples. The first one is one binary modulator. So in the binary modulator A, my signal set is just, this is my S1T. And then this is my S2T. Is that okay? So with this design, the output, if you observe the output of the binary modulator with this specification, then you will see that the output waveform will be like this. So this corresponds to a bit sequence of 0, 1, 1, 1, 0, 1. Is that okay? 6 symbols. Now, in the second lower figures, the lower figures is another design, design B, where my two waveforms will be given by smooth pulses. Okay, so that will be a design B. So using design B for the same input bit sequence, 0, 1, 1, 1, 0, 1, the output waveform of the binary modulator would look like this second figures. Is that okay? So likewise, any one of you can dream up or can design your own binary modulator. You just need to think about two different waveforms, which is not too difficult, to put in your so-called signal set. So this is called the signal set. Okay? So designing a binary modulator is never a challenge. Of course, any one of us can dream up different binary modulator, but some will have a better performance than the others. We'll talk about performance later on. All right? Is that okay? Now, so based on this operation, so once you define or once you specify the symbol duration and you specify the signal set for the binary modulator, there is no more freedom behind the binary modulator. The operation and the performance will be well defined automatically. No more freedom in the design. Okay. So with this simple design, let's look at the performance. We introduced two performance metric and two resource metric, right? So for this design, let's look at, for example, the bit rate. Can we talk about the bit rate? Are we ready to talk about bit rate? Bit rate is defined as number of bits that can be delivered over 1 second, right? So with this operation, as we just talked about, we can talk about bit rate, right? How fast the information, how fast the bits are sent to the other side, right? So what is bit rate? Over 1 second. Well, just give you some number. For example, in my binary modulator, symbol duration is 1 millisecond. Then over 1 second, how many symbols will be transmitted? 1,000, right? 1,000 symbols. So obviously, this is the bit rate. Is that okay? Just think about if a symbol duration is 1 millisecond, then I measure 1 second interval and I count how many symbols are there. And obviously, we'll expect 1,000 symbols, right? So that means the bit rate is 1,000 bits per second. So in general, bit rate will be 1 over TS bits per second, right? Remember last time I mentioned there is always a misconception that bit rate, how fast the bit can be delivered, has nothing to do with how fast signal travel, right? Remember that? So now you can see clearly, bit rate depends on the symbol duration only. It has nothing to do with how fast the signal travel on the channel. Is that okay? How fast the signal travel on the channel only determines the propagation delay, but not the bit rate. Bit rate depends on the symbol duration. Is that okay? All right, so now this is our bit rate. Then can we talk about bit error rate? Error probability at this point? No, right? Because obviously the error probability depends on the receiver design as well. We haven't talked about the receiver, right? Just talk about the transmitter. So how can we talk about the error probability, right? Now, okay, then in the resource metric, can we talk about the bandwidth? Yes, the bandwidth is depends on this the Fourier transform of these symbols that we design, right, into the signal set. So remember, again, without going through the actual Fourier transform calculation, remember last time we talked about bandwidth, there were two factors that affect the bandwidth, right? Which two factors? The first one is the pulse shape, right? Do you have any, if you look at the time domain waveform, do you see any sharp transition, sharp corners like this? Or do you see a smooth pulse like this, right? So that will affect the bandwidth. Those waveform with sharp transition, discontinuity, that will generate high frequency components, right? Okay, that's number one factor, the pulse shape. Number two factor is what? The symbol duration, right? Remember, there's a trade-off between bandwidth and symbol duration. If you squeeze the bandwidth, the symbol duration will be expanded. If you squeeze the symbol duration, the bandwidth will be expanded, right? These were the two factors. So in general, bandwidth, you have two factors, right? So let's introduce some parameters. This alpha account for the contribution due to the pulse shape. Okay? If you have a discontinuous waveform, you're going to have large alpha. Okay? On the other hand, if you have smooth waveform, your alpha can be as low as 0. Okay? And then the second factor is a trade-off, like this. Okay? So in general, if you really compute the bandwidth, you will find that the bandwidth will depend on these two factors. Okay? Now, if you consider these two designs, design A and design B, they have the same symbol duration, right? So the second factor will be the same. Then which design will have a larger bandwidth? Of course, this design will have a larger bandwidth because the alpha for the design A will be larger because the waveform for design A contains sharp transitions, discontinuity, right? Whereas for design B, it's a smooth pulse. So your alpha will be very, very small, okay? So this alpha is account for the pulse shape. All right? Now, just based on this two, can you see the trade-off between bandwidth and bit rate? Now, if I'm able to increase if I want to increase the bit rate, put it this way, what can I do now? I can increase this term, right? So I can decrease the symbol duration. If I reduce the symbol duration into half, instead of 1 millisecond, I reduce it to 0.5 millisecond. Then the bit rate will be doubled, right? But at the same time, my bandwidth will also be doubled because of this factor. Is that okay? So what does that tell us? That means there is a trade-off between bandwidth and bit rate, right? This is exactly the first direction. If I increase bandwidth, I can increase bit rate. Is that okay? Now, so symbol duration, this term, basically plays a role as a trade-off, right? If I want to have large bit rate, I want to have small symbol duration. But if I use a small symbol duration, my bandwidth is also large, right? So basically, that would be a fair trade-off between bit rate, which is your performance, and bandwidth, which is your cost. Is that okay? What about this term, alpha, for the pulse shape? Is there any advantage of using an ugly pulse like design A, where you get a large alpha? If you use the design A, you will get a large alpha. So bandwidth cost will be higher, right? But do you get any benefit? Bit rate doesn't depend on your alpha, right? So there's no benefit. So because of that, usually, we will not prefer design A. Okay? And in practice, if you look at the data sheet of some chipset on the transmitter side, if you look at the baseband design, there will be a stage called pulse shaping filter. This pulse shaping filter is actually to smooth your pulse so that you don't transmit something like this. You transmit something like this. Because designed like this, it will cause large alpha. So alpha A will be large. But this large coefficient wouldn't translate into any performance benefit. So that would be, so there is no motivation of sending out a pulse that is not smoothed. Is that okay? So now without loss of generality, we will assume we always have a pulse shaping filter so that we will never go with this design A. We'll usually send out some smooth pulse. Okay? So we can pretty much ignore this factor, assuming we have a pulse shaping filter in the process. So therefore, we will just, with this assumption, we'll just say that the bandwidth is given by this, under the assumption of smooth pulse. Okay? Because there is no real advantage of sending non-smooth pulse. So usually we will have a pulse, even if your original design is not smooth, before you transmit onto the radio channel, you always have a pulse shaping filter to smooth out the pulse. Okay, so therefore we just assume you have a smooth pulse design in your signal set design so that the bandwidth will be given by this. Is that okay? So with this, you can see clearly this is a trade-off. If I double my bandwidth, I will double my bit rate. So that's the fair trade-off. Okay? So I can talk about bandwidth. What about power? Am I ready to talk about transmission power? of course, right? So this defines the transmitter. The signal set defines the transmitter already. So the average energy is given by, we have assumed 50% of the chance input bit is 1, 50% of the chance input bit is 0. So half and half. Then the average symbol duration will be 1/2. The energy you will have to spend when you transmit S1, right? So let's call this E1 plus E2. That will give me my average symbol energy, right? So my average power will be simply the average symbol energy divided by the symbol duration. Is that okay? So obviously your average transmission power depends on your signal set. Is that okay? So now with this simple black box approach, with these two parameters behind the black box called binary modulator, we can already talk about the three metrics: the bandwidth metric and the power metric. Okay, these are two cost metrics in the performance. And then we can also talk about one of the two performance metrics, which is a bit rate. Of course, we cannot talk about bit error rate yet because obviously bit error rate depends on the receiver as well, and we haven't talked about receiver. Is that okay? So with this, the message we got is, if I want to double the bit rate, I can double the bandwidth. So we can see this part of the trade-off. Okay? A natural trade-off, which should be easy to understand. All right? Now, with this, let's go back to the drawing board and ask, can we do better than this? We want to increase the bit rate always, right? Because that's a very important performance metric. Let's say, can we increase the bit rate without increasing bandwidth? I just have this fixed bandwidth. Okay, this is confined in my license. Okay, so I cannot increase the bandwidth anymore. Is there any other ways that I can increase the bit rate without increasing bandwidth? Okay, now we go back to the design. So in this design, once again, every symbol duration, we take in one bit, look at this bit. If this bit is 1, we transmit one symbol. If this bit is 0, we transmit another symbol, right? We do this bit symbol by symbol this way. But why we have to confine ourselves to look at one bit at one time? Can we look at 2 bits at one time? Understand what I mean? Now let's say I modify the design. I modify the modulator design so that on every symbol duration, now I take in 2 bits. I take in 2 bits at one time. Then can I still design a modulator that accommodates this? If I take in 2 bits at one time, what kind of modification do I need? Suppose I do not want to increase the bandwidth, right? So this symbol duration is not changed. It's the same, right? So my cost is the same. Now, if I take in 2 bits at one time, then what about my signal set? Do I need to modify my signal set? Yes, right? Because previously in the binary modulator, every time I take in 1 bit, and for 1 bit I only have 2 cases, right? So that's why I need 2 members in my signal set to differentiate these 2 cases, right? Now, if I take in 2 bits at one time, how many cases are there? 4, right? Each bit has 2 cases, so 2 times 2, I have 4 cases, right? 0, 0, 0, 1, 1, 0, 1, 1, 4 different cases. So in order to differentiate 4 cases, I need to expand my signal set. Instead of 2 members, I need to have 4 members, right? So I just need to dream up 4 different waveforms and put into my signal set. Is that okay? That's not too difficult. I just need to dream up 4 different waveforms, right? And then I put a bit label behind each of these waveforms. For example, this is used to represent 0, 0. This is used to represent 0, 1, 1, 0, 1, 1, for example. All right? So I can do this, right? If I do this, then that means the output symbol, the output signal generated by this modulator will be given by, I would output S1T if the input bit pattern is 0, 0, right? I would output S2T if the input bit sequence is 0, 1, etc., up to S4T. Is that okay? So the operation would be just slightly modified. So I have 4 possible waveforms in my output, depending on the two input bits combination. Is that okay? Now, since I have 4 members in my signal set in this case, I don't call this binary modulator. I call this quaternary modulator. Quaternary means 4, okay? So named after we have 4 members in the signal set. Now, with this quaternary modulator, let's revisit the formula. What is the bit rate now? So 1 over TS this time give me what? Give me over 1 second window. How many symbols are delivered, right? But now, different from the binary case. In this case, every symbol carry how many input bits? It carry 2 bits, right? So the total bit rate is 2 times this factor. Can you see that? Okay, so as an analogy, a symbol is like a minibus. Okay, in the binary modulation case, the bits are like the passenger. In the binary modulation case, a symbol, so-called the minibus, only have 1 passenger seat. Okay, so this term determines 1 over TS give you over 1 second how many minibus leave the transmitter. Okay, and since 1 minibus only have 1 passenger seat, the number of passengers leaving the transmitter is also the same as 1 over TS in the binary case. Okay, but in the quaternary case, what we have modified is every symbol now carry 2 bits, right? This is the same as the minibus. Every minibus has 2 passenger seats. Is that okay? So 1 over TS still gives you the number of minibus leaving the transmitter every second. Okay? But now, since every minibus have 2 passenger seats, bit rate refers to how many passengers leaving the transmitter over 1 second. So that's why there's a factor of 2 here. Is that okay? Now, bandwidth, for the same idea, for the same reason, bandwidth is only given by 1 over TS, assuming smooth pulses, assuming all these members are smooth pulses. Okay? So bandwidth is still given by 1 over TS, which is the same as before. So by this modification, what have we done? We have doubled the bit rate, right? Without increasing bandwidth. Can you see that? So this is amazing. Now, of course, the average power also needs to be modified. Instead of 1/2 in this case, we have 4 possibilities. So it will be 1/4. Like this. Is that okay? So 25% for each combination. So that would be the modification needed when we upgrade to quaternary modulation. Is that okay? Now, sounds too good to be true, right? So what I have demonstrated is, for the same bandwidth, I can double the bit rate, right? But now, if you understand this trick, can you further increase the bit rate? Seems yes, right? Why do I have to constrain myself? Why do I have to tie my hands to look at 2 bits at one time? Can I look at 3 bits at one time? Now, if I do this, what do I need to modify? If every symbol, this black box, take in 3 input bits, what do I need to modify? My signal set, right? Previously, I only have 4 members. But if I take in 3 bits at one time, how many possibilities are there? 2 times 2 times 2, 8 possibilities, right? So 4 members is not sufficient. So in this case, I need to modify into 8 members. Okay? And then again, similarly, I put a label behind each member. For example, this is used to represent 000, and this is used to represent 111. And then my output logic is the same as before. I will output S1T if the 3 bits are 000, this is 001, etc. Is that okay? These will be my only modification. And since I have now 8 members in my signal set, this is called A-ary modulator. Now with this modification, what would be the bit rate? Using my minibus analogy. For the same symbol duration, the frequency of my minibus is the same. Okay? If let's say this is 1 millisecond, so that means over 1 second window, I still have the same number of minibus, 1,000 minibus leaving the transmitter. Okay? What is the difference now is every minibus have 3 passenger seats. So when I'm asking for the bit rate, I'm asking for how many passengers can I deliver over 1 second window. So in this case, this becomes a 3. Is that okay? The others remains to be the same, except that is 1/8, and this is the average over 8 possible symbols. Okay? So bandwidth is still the same as before, but now I have increased the bit rate by 3 times. And if you learn the trick, I don't need to restrict to 3 bits at one time, right? I can continue the logic. In general, if I have M signal members in my signal set, okay, then I can take in log to the base 2 of M, this many bits at the input. Is that okay? So in general, and then that will be called Emery modulator. With Emery modulator, my bit rate becomes log to the base 2m times this factor. This factor log to the base 2m denotes the number of passengers per minibus. How many passengers can I squeeze into a minibus? And this second factor give me how many minibus leave the transmitter over 1 second. So 2 together give you how many passengers leaving the transmitter over 1 second window, which is the bit rate. Okay? With this modification, it seems to suggest that for the fixed bandwidth budget, however small this is, I can still increase my bit rate to any large level that I like by just using a large M. I can keep on increasing this M to achieve a higher and higher bit rate, right? Without any cost. Right? So this picture is telling us this message. So if this is true, then that means there is free lunch. Okay? Which should contradict to your common sense, right? You should know there shouldn't be any free lunch, right? If there is free lunch that works this way, then bandwidth will not worth anything, right? Because however small bandwidth you have, you can scale up the bit rate into any higher level you like. So the real question is there any penalty? Or what is the penalty? What is the cost behind using a large M? Emery modulation. Now for those of you who have studied with WE background, you probably have studied Emery modulation as well. So what's the cost of using a large M in the Emery modulation? Now what I've shown here is the bit rate can be increased to any level you like. Bandwidth stays the same. So no cost, and I can increase the bit rate to any level. This seems to be too good to be true, right? So what is the hidden cost? The hidden cost is because you have this illusion, simply because we haven't talked about the bit error rate yet. And we are not ready to talk about bit error rate because we haven't talked about the receiver, right? Obviously, bit error rate depends on the receiver. But then when we talk about the receiver, after we talk about the receiver, and then we talk about the bit error rate, you will have the overall picture, holistic picture. By then, you will see that the penalty of just increasing M this way would be higher error probability. In the analogy, that is, if you squeeze too many passengers into a minibus, the rate of accident to the minibus will be higher and higher. Okay? So that is the hidden cost. We couldn't see this hidden cost because we haven't talked about the error probability. So we have an illusion. Seems to suggest it's free lunch, but indeed there is no free lunch. Is that okay? All right, so let me summarize. So that is basically the digital modulation, Emery modulation in general. Okay, so you can think of that as a black box. So you can easily design your own Emery modulator. It's not that difficult. You just need to specify these 2 parameters. First one is a symbol duration, which is just a number. Second one is the signal set. You just need to use your creativity to think about m different signals into your signal set. As long as they are different, then that would be fine. They can function as a memory modulator, and then they will have these performance metrics. Is that okay? So, all right, so this is the general memory modulator. So therefore, as I said, there are two important parameters. First one is the symbol duration. The symbol duration gives you the so-called baud rate or symbol rate. So there are different terms for this. Somebody call this baud rate, somebody call this symbol rate. So it's just the same. It's talking about how many symbols you can deliver over 1 second window. Okay, it's the number of symbols per second. And this is proportional to the bandwidth. Okay, the baud rate or symbol rate is proportional to the bandwidth cost. Okay, so if you do not want to increase the bandwidth cost, that means you are not allowed to change the symbol rate. Okay. The second parameter is the signal set. The signal set consists of m different signals, okay, as members. So now if I have designed my own memory modulator, that means I will have my specification, a symbol duration, and my signal set. So how do I communicate my specification to you? Now, symbol duration is easy. It's just a number. Maybe my symbol duration is 1 millisecond, so it's easy to communicate. But what about my signal set members? My signal set, my design, has this particular signal set with this m members, right? So how do I specify this, my design to you? There are two ways. For example, I design my quaternary modulator. So I have 4 members in my signal set. So one way that I describe to you the signal set is using time domain approach. So draw you the 4 waveforms. So these 4 waveforms, S1T, S2T, S3T, S4T, the toy example we come across last time. So these are the 4 members of my signal set. That's one way to specify my signal set, okay? A second way to specify my signal set, more abstract, is using a geometric domain, right? So I define the basis, right? Remember last time we talked about geometric domain representation? So I define my basis, and these 4 signals require a 3-dimensional space, right? With 3 basic Legos to span a space big enough to contain these 4 guys, right? And then based on these 3 bases that we define, or for normal basis that we define, the 4 signals appears as 4 points on this signal space. Is that okay? So this is my second way to define to tell you my signal sets, right? I can tell you that my signal set consists of these 4 members. These 4 members appear as 4 points in this space. Full stop, right? So now, in the literature, there is a name for this. This is called constellation diagram. So for those of you who studied EE before, you should have heard about this at least, right? Constellation diagram. So now, you shouldn't be too scared to look at it, to see this term. These are nothing but just a geometric domain representation of the signal set. If you find it difficult to swallow, you can just think about, okay, I'm just trying to describe to you my signal set members, okay? So if you don't like this constellation diagram, you can always go back to the time domain. That is, my signal set has these 4 different waveforms, okay? It's the same idea, conceptually. But later on, you will find that there are some reasons why people prefer using constellation diagram to describe the signal set members, okay? I will leave it to later discussions after we talk about the receiver, okay? Now, if I happen to, at this point, I can use the time domain specification or geometric domain specification. Either way, I'm talking about what are the members in my signal set, okay? So I'm just communicating these second parameters behind my memory modulator, okay? That's the only purpose. Time domain, geometric domain doesn't make much difference. It's just a personal style, okay? Think of it this way. Now, if I happen to describe my signal set members, the 4 members, using 4 points in the constellation space, or on the signal space, then what is the average energy? Average symbol energy becomes, remember, the distance of a point from the origin square gives you the symbol energy, right? So therefore, if I specify my signal set using this constellation diagram, then the average symbol energy will be the average of the square of the distance of the points from the origin, given by this, okay? Of course, if I specify my signal set using time domain waveform, then the average energy is you have to compute the individual energy from a time domain equation. Okay? Take the S1t square, integrate over a symbol. That gives you E1. Okay? So that would be the modulator. Is that okay? Hopefully, this is simple enough that you don't need to worry about the detailed generation. And in particular, if you have double E background, you may heard about something called IQ modulator. Have you heard about that? IQ modulator. You have people talk about digital modulation. You also have an I branch and Q branch and a mixer, blah blah blah. So we don't need to worry about this detailed mechanism. The IQ modulator is just a special case of the two bases for a two-dimensional space. You can call the x-axis the I, y-axis as the Q. Okay, so these are just two basis functions that span a two-dimensional space. And then people call the first axis I, call the second axis Q. It's just like this. Okay, but of course our signal space does not need to be two-dimension. Sometimes it can be three-dimension, it can be m-dimension. All right. Okay, I guess we are good on this, right? So now the remaining metric we cannot talk about yet is the error probability. And to talk about error probability, of course, we need to talk about the receiver. So let's continue our journey to talk about the receiver so that we can fill up the missing parameter, error probability. Okay. Now again, for the receiver, I also like to use a black box approach so that we don't worry about the detail inside the black box. We understand the whole thing from top level. Now, so the receiver is like this, or demodulator. So again, a black box with an input and output. The output would be the output of the receiver is the guess what could have been transmitted behind this symbol, right? The input to the receiver would be usually a noisy observation. A noisy observation of what could have been transmitted. Okay? So to give you an idea, so because we consider additive White-Gaussian noise channel, right? So the input observation, so this is an observation to the receiver. So you just imagine yourself as a receiver. Okay? Your task is to give me your guess what could have been transmitted in this current symbol, right? So you are given a certain noisy observation. So let's say, as an illustration, let's say my signal set design in the transmitter is like this. So let's say this is my modulator. Okay, I could only transmit one of these two waveforms, S1t or S2t. It's a binary modulator. Okay, so now let's say this is associated with bit 1, this is associated with bit 0. Okay, so let's say this is my binary modulator. And then based on this binary modulator, I send you a symbol. Either the symbol will be either S1 or S2. No other possibility, right? So now when the signal reaches to you, you are the input, you are the receiver. At your input, because of the noise, what you observe is not this one or this one. What you observe will be a contaminated waveform. For example, something like this. Okay? Now, let me give you an easier example. Suppose the noisy observation that you observe is something like this. Okay, let's say I give you three symbols. This is the first symbol, this is the second symbol, third symbol. Let's say this is the observation. Okay? Then, now you are the receiver, right? Then can you guess what could have been transmitted in the first symbol? 1, right? And this is also 1, right? And this is 0, right? You probably can guess this is 1, 1, 0. Right? Okay? Now, this is the best case, or a very good case, because you can still recognize the form of the waveform, the form of the transmitted, the two possible transmitted waveform, right? It's only slightly contaminated by noise. In technical language, this corresponds to very high signal-to-noise ratio. Okay, so that's why it's easy to any of you. But let's say the signal-to-noise ratio is not that high now. The signal-to-noise ratio becomes moderate. And then this is your observation. Now with this observation, again, imagine yourself as a receiver. Can you easily guess what could have been transmitted? Probably not, right? Not that easy. Is that okay? And let's say we are not only interested in designing any receiver that can work, we want to design a receiver that has the best performance, optimal receiver. Optimal receiver means the receiver you give me will have the smallest error probability, right? Okay, let's say this is our goal. We want to find the best possible receiver. Then this is even more challenging, right? You don't know how do you do the output, right? How do you do the detection based on this very noisy observation? Now this is what happened in time domain. In time domain, usually we don't have, it's not that easy to extract insights for the detection problem. Last time when I introduced the geometric domain approach, right? I explained how you do it, right? But I haven't explained why we want to do it, right? Why we want to go through all the trouble to represent signal waveform as a point in some abstract space. What's the point of doing this? So here we will see the reason. The reason is because as a normal person, if you work on time domain, it's, for those of you who have double E background, if you remember how you study digital modulation and demodulation and how you analyze the error probability, you go through, most of the time I think you will go through this algebraic approach. You have, many equations in the analysis before you can get the bit error rate expression, which is the Q function of something, right? So those are algebraic approach. And for a normal person, it's not that easy to develop insight from these algebraic equations. However, if you have this geometric domain representation of signals, you can turn this detection problem into a geometric problem. And average person will be able to develop intuition based on a geometric problem, right? Much easier than developing insight for algebraic equations. So that's the reason we want to talk about how we represent signals using geometric domain, okay? So the so-called geometric domain insight, intuition will be, you will find what I mean in a minute, okay? So now, okay, so this is what happened in time domain picture. If you look at this receiver design from a time domain angle, this is the task, a difficult task for you to design. You are given a certain noisy observation waveform in time domain. How can you design the receiver that can give the smallest error probability? Okay, it's not that easy to construct the receiver. Now, what about if we look at this, the same process from just another angle, from a geometric domain angle? From a geometric domain angle, what happened would be, instead of looking at this in time domain, we'll represent everything using vector, a point in some signal space, right? So let's say we have defined, remember last time, to convert a time domain waveform into geometric domain, remember there were two steps, right? The first step is to find the basis, find the orthonormal basis that can define a space big enough to contain the signal we are interested, right? That's the step one. Step two is talking about, based on this coordinate reference, how do we work out the coordinates of individual signals, right? Which is doing a bunch of projection using inner products, right? Okay, so let's assume we have gone through step one. So we know what is the signal space. Let's say the signal space is this two-dimensional picture. Is this on this whiteboard, okay? So this two-dimensional space will be big enough to contain the signal set members, okay, in the modulator, to contain these two guys, okay? So based on this two-dimensional signal space, we can express everything in terms of a two-dimensional vector, right? So the receive point, receive vector, will be equal to the transmitted vector plus a noise vector, right? That's just using a geometric domain angle to look at the same process that happens in the channel, right? So this is the receive point, this is the transmitted point, and this is the noise vector, everything in vector. Now, what do we mean by noise vector? Now, again, from high school mathematics, a vector actually have two attributes. One is the length, right? The other is the orientation. The other is orientation, right? So this is a noise, a noisy vector, put it this way. That means this vector is random. What do we mean by a random vector? Number one, the length is random. So this time you look at the realization of noise vector, it may be of this length. Next time you look at the realization, it may be this long. The length is random. Also, the orientation, where the vector is pointing, is also random. Okay? Now, since we are shown the noise is white Gaussian noise. White Gaussian noise means, after some math, I'm not going, don't worry about the math. But white Gaussian noise, after some math, when you convert a white Gaussian noise to a vector, you will find that the orientation of the vector will be isotropic. That means it will have equal probability of pointing at any direction. Is that okay? So that's the properties of this noise vector from the additive white Gaussian noise. Okay? Number one, the length is random. Number two, the orientation is isotropic, equal probability to point to any direction in the space. Okay? So let's look at geometrically what would happen to the transmitted vector. Now, let's say this is a two-dimensional space. This is my first basis, this is my second basis. Now, as I said, some textbook will say this is the I, this is the Q. Okay, it's just a label. So now we have the two-dimensional space. Now, without noise, if there is no noise, we know that if this one is 0, right, we know that the transmitter can only transmit two possible points, right? So let's say this is S1 and this is S2. Okay? There are only two possible members in my signal set, right? So if there is no noise, then you know that the receive point, the receive vector, would only be either here or here. No other possibility, right? Is that okay? Because if the noise is 0, what else can you observe, right? Either it's given y equal to s, right? S can only take either S1 or S2 by the design of the modulator we just talked about, right? So without noise, your observation, your y, would either be this point or this point, right? But now we have non-zero noise vector. So let's look at where will the observation be? Now suppose we transmit S1, okay? What you receive is S1 plus a random vector. So this random vector, as I said, geometrically, that means it has a random length and random orientation, right? So maybe this is my receive point. Okay? This is saying that why my receive observation would be here? That's because if S1 is my transmitter point, this is my transmitter vector plus a noise vector. Okay? So that brings the observation to here. If in the next symbol I still can't transmit S1, then where would be my second observation? My second observation depends on the random realization of this noise vector, right? So my second realization may be here, right? That corresponds to a noise perturbation up here. Is that okay? Now, if you continue on this, let's say you transmit 1,000 symbols, which is S1. You transmit 1,000 times S1. But each time your received observation will land on different location. Okay? So on average, what would be if you try to mark down the received location of this 1,000 transmission, the received observation will be lying somewhere within a certain noise cloud. Is that okay? Now, why noise cloud? Because, as I said, this random noise vector is isotropic. It has equal chance of pointing at any direction. So by symmetry, you will have the dispersion of the receive vector will be spherical, right? Spherical symmetric because of the isotropic properties of this noise vector. And also, there is an average size of this noise cloud, right? The average size is determined by the average length of this noise vector. And remember, the average length square gives you power, right? So, therefore, for a given noise power, it will determine a certain size of the noise cloud. In other words, when the noise power is higher, the noise cloud will be bigger. Is that okay? That's a geometric association. So with this, hopefully we can visualize what would be the received observation on the signal space. given the perturbation of a random noise vector. Okay? So it will be spherically symmetric, center about your transmitter point. Okay? And the size of this noise cloud depends on your noise power. Okay? That's the three important geometric intuition. So what I have drawn here is a two-dimensional picture. In the NOx, this is a three-dimensional picture. Is that okay? If your space is three-dimensional, then the center of the noise cloud would be your transmitter point. But then the size of this three-dimensional sphere, noise sphere, would be basically determined by the noise power in the same way. Okay? And this is, in a three-dimensional space, this is also spherically symmetric, meaning that the noise vector will point in any directions in the space with equal probability. So that's the spherical symmetric. Is that okay? So this is the visualization of the received signal. If you look at this from geometric domain, okay? And remember, we didn't change anything. We just changed the angle. We look at the physical process. The physical process is still the same way. You transmit a certain signal across a noisy channel. That's the physical process. Previously, here we look at this picture. We look at this process from a time domain angle, and that would be your noisy observation waveform. But what we have done here is just changing the angle to look at the same physical process. We are not changing the physical process itself. Is that okay? So when we change the angle, that is, look at the same physical process from a geometric domain angle, this is what happened. You transmit a certain point at the transmitter, S1, but your receive point will lie anywhere within a certain spherically symmetric noise cloud. The size of the noise cloud depends on the noise power. That's okay, right, everybody? All right, now let's look at two questions. The two questions we want to discuss is, number one, how should we design this receiver, right? That's the first topic that we were talking about. How should we design not only any receiver, but the best possible receiver, okay? The design of the demodulator, okay? Given a certain noisy observation, how do we generate the output, okay? Second question is, then what is the error mechanism? Even if we design the best receiver will still make mistakes sometimes, right? We want to also analyze what's the best case error probability, what's the error mechanism, okay? So these are the two goals we're going to talk about. So let's focus on the first goal first. How should we design this receiver? Now let's say, again, for the binary modulator, for this same modulator, let's say this is the corresponding signal set geometric domain representation for S1T, okay? And then this is S2T. So once again, if there were no noise in the channel, then the received observation could either be this or this, no other places, right? But because of the presence of noise, the receive point can be anywhere on the space. Is that okay? So now, let's say I give you one noisy observation. The noisy observation may be here. This is my observation. Now in this case, you don't know what could have been transmitted. The transmitter could have transmitted S1 or S2, but you don't know which one. Okay? What you know, now imagine, each one of you imagine yourself as a receiver. Just use your intuition. Once again, okay, I'm the transmitter. I can only transmit either S1 or S2, no other signals. Okay? But the fact that your observation now becomes here, you don't know which S1 or S2 could have I have transmitted behind this observation, and your task is to tell me your guess, okay, based on this observation. Now with this, what would be your guess? You guess towards S1, right? Why? S1 is closed. It's the hypothesis testing problem, right? Given this observation, you know there are only two possible transmitted signal behind this observation. Case 1 is this, case 2 is this. And then you want to pick the most probable case, right? That's the logic behind this. Turns out that intuitively, you will pick this one because this one is closer to this one, right? Now, and this makes a difference. Closer means higher probability, okay? So therefore, you should pick this one because this is closer to your observation, okay? So what is the logic behind? It's very simple. You measure two distances. This is one distance between the first hypothesis and the observation. You measure another distance. This is the second hypothesis with your observation. And you pick the one that gives you smallest distance in Euclidean distance sense. Okay? Now, why this is the most probable choice? Most probable choice. You can think of this in terms of the noise vector. Given that this is your observation. Now, if S1 was the transmitter symbol, what it takes to get the observation to here? You need a noise vector like this to bring the observation to here, right? Now, if S2 was the transmitter symbol, what it takes to get the observation to here? You need a noise vector like this to get the observation to here, right? Now, so therefore, as I said, this is a random noise, right? The noise vector, the length of the noise vector follow a distribution, okay? The larger the length noise vector is, the smaller the probability. That's the nature of this distribution of the length vector. So the PDF and the length of the noise vector square is like this. Okay? So for the case 2, for the second hypothesis, it takes you this length of noise vector, which is highly unlikely compared to case 1. Case 1 only take a much shorter noise vector to explain this observation. Is that okay? So to explain this observation, the higher probability explanation would be S1 instead of S2. Is that okay? So that's the logic behind choosing the closest hypothesis to your observation. That's the logic behind. Okay? And this turns out to be not only a reasonable receiver, it's actually the best possible receiver. You may dream up other logic to do the detection, but the error probability will not be better than this simple detector. Is that okay? And this is called minimum distance detection. Or minimum distance demodulation. In mathematical language, this design is given by what you are trying to do is this output detection, output of your demodulator is given by arc mean of your S. Your S only have, in general, M choices. If I have an M remodulator, I will have M choices, right? And what do I minimize? I minimize the distance between the observation and the hypothesis. This simple equation summarizes the logic behind this receiver. Now, if you cannot comprehend this, so I guess you know what is minimum, right? But arc mean, okay. In your high school mathematics, I guess, if I ask you to do this, this one, the minimum of a function of x with respect to x, this returns the minimum function value. Is that okay? But sometimes I'm not interested in the minimum function value. I'm interested in the minimizer, right? I'm interested in the x that achieve this minimum function. Then in that case, I should say this. So this is the difference. Minimum returns the minimum function value, but arc mean returns the minimizer. Can you tell the difference? Okay. For example, if fx is a quadratic function like this, let's say fx equals x squared plus 2. Okay. So this is 2. Then the first equation, the f star returns what? 2, right? So this one would be 2. So second equation, what does that return? 0. The minimizer is 0. Is that okay? So now, same here. We are solving a minimization problem. Our objective function, our fx, is now the distance between the observation and the hypothesis. Now, the hypothesis cannot take any value. The hypothesis S can only take one of these M values, right? Because that's the design of the M-ring modulator. At the transmitter symbol cannot be arbitrary. The transmitter symbol can only be one of the members of the signal set, right? Okay? So, and then I'm not interested in the minimum distance value. I'm interested in the symbol that achieved, or I'm interested in the hypothesis that achieved the minimum distance. That means I'm interested in the minimizer. Is that okay? The minimizer will be the output of the receiver. So that's why this is what this equation tells us. Is that okay? All right? No, so that also demonstrates that the receiver needs to know the signal set. This receiver needs to have the side information about the signal set. If the receiver doesn't know about the signal set of the transmitter, there is no way it knows the hypothesis. Okay? So this is assuming you as a receiver, you know what was my signal set when I transmit the symbols to you. Okay? So this is the minimum distance demodulation. Now, of course, this is one equation, but then as an engineer, how do we implement this equation, right? Into suppose you want to build an ASIC, you want to do a chipset design that implement this equation, then what should we do? So let's look at the what we call architecture design behind this receiver based on this so-called algorithm. And by the way, to explain this, you may not know about the terminology, architecture, algorithm, blah, 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 blah. Now, okay, imagine after you graduate, you want to join a high-tech company doing chipset design, okay? So in an R&D branch of a chipset design company, you have, roughly speaking, three important levels of engineers. The first level is what we call developer. Developer means it can be hardware developer, it can be software developer. Okay, hardware developer, in this case, maybe you should be hands-on in Verilog or VHDL, right? Digital logic design, that sort of skills. Software engineer or software developer means you will be proficient about Python, C or C++, whatever. So the task of this developer is somebody give you a module with a specification, with a certain algorithm. You need to implement using either hardware or software. Okay, so I guess that's you guys should be very good at that at this from your mainland education. Usually, this is a bachelor or a master of science or master of philosophy. So usually these are the requirements. Okay, so you guys will, if you want to join a chipset company, R&D branch, you probably can work as a developer if that's what your interest. But above the developer, there's another layer. It's called system engineer. This system engineer usually requires PhD level. And the task of the system engineer is to design algorithms. So, for example, this is an algorithm. Suppose we want to design an optimal receiver, okay, an optimal receiver. Then if you work as a system engineer, you have to go through the mathematics and derive the algorithm for the receiving, for the detection problem. And let's say after all this analysis, you find that this is the optimal receiver, okay? And the algorithm, the so-called algorithm, is now summarized by this mathematical equation, okay? That would be the output of a system engineer, okay? But that's not the most important. The most important or most highest salary is usually somebody called architect. The architect can be from developer, can be from system engineer, but they must have, they need to have a good number of years of experience, and they need to understand both the algorithm and the implementation constraint, okay? So this architect is responsible for taking this kind of algorithm and map it into implementation, partition different tasks into different blocks and with a holistic consideration, okay? So, of course, the architect requires good experience, good understanding of the algorithm and implementation constraints so that you know what are the implementation implications when you map to different modules. Developer usually will just take a particular block and then implement the block and deliver the implemented block to the next level. Okay. So, and of course, architect is in a team. Typically, you only have 1 or 2 architects, and the architect, of course, worth very high salary. Okay. Now let's try to use this example and try to let's pretend to be an architect. Okay, and walk through what is the task of an architect from using this example. So suppose your system engineer give you this algorithm, a very simple case. Okay, so this is what you should do for minimum distance demodulation, for optimal demodulation. This is what you should do. And then you comprehend this so-called algorithm. You as an architect, you try to map this into implementation. Suppose you want to build in a chipset for this. Okay, you want to map into an implementation block diagrams so that the developers can implement. Okay, so there are always different ways to map into implementation. Let's try number 1, the first way. Okay, so your receiver input is a noisy observation, which is a waveform, right? So you know that you need to compute this distance metric, right, in order to solve this minimization problem. So first stage is, okay, this distance metric requires geometric domain representation, right? So the first stage is you probably need to convert from time domain to geometric domain, right? So how do you convert this? Remember, let's say we have a 2-dimensional signal space only. Okay, remember from last time you have a step 1 and step 2, right? So now step 1 is done. So we know what are the 2 bases, phi 1t and phi 2t. Now step 2 is to find the coordinate, right? So this y has 2 coordinates. How do we find out the 2 coordinates? Geometrically speaking, we are going to do a projection, right? And algebraically, projection is a bunch of inner product, right? So what we should be doing is an inner product of this yt and the first basis. That gives me y1, right? And then the second coordinate would be the inner product of yt and the second basis. That gives me the second coordinate. Is that okay? And what is this inner product, once again? As we talked about last time, they are nothing but just an integrator or correlator. Okay, so the first block is to have this correlator to correlate the received waveform with the first basis. And the second block is a correlator to correlate the received waveform with the second basis. Is that okay? So this is the stage 1. Stage 1 is nothing but just conversion from time domain to geometric domain. Is that okay? After stage 1, then I have the coordinate of the y, right? Then I need to compute this metric, right, for this minimization problem. So how do I compute this metric? This is my y. So I have, in general, M hypothesis, right? So S can take S1, S2 up to Sm, right? M possible choices for S. So I need to compute for each case what is the Euclidean distance, right? So I need to compute this and the second metric, and then the M metric. Is that okay? So I compute the distance of the first hypothesis to my observation, distance of the second hypothesis to my observation, blah, 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 blah. Well, I compute M distances, right? That is the stage 2. Stage 2 is to compute the distance metric, right? So in terms of implementation, where would you compute this? Would you do it in the analog domain or digital domain? We just think about, if I ask you to, well, obviously, right? So you know the Euclidean distance, you know the coordinate of y, you know the coordinate of S1, right? You think about, if I ask you to write a C program to compute this would be pretty straightforward, right? But if I ask you to build analog circuit to compute this is not that trivial, right? So obviously, you would like to compute this on a, for example, processor, on a digital signal processor. If you don't have a processor, you may not like to compute this using digital logic, right? FPGA or chipset. Is that okay? Anyway, so this is the second stage where you have computed m distance matrix. At the end, what do? You want to pick the minimum, right? You want to find the minimizer. Then how should you do it? You need a first stage. The first stage is how do you find the minimizer? I give you m numbers. I give you m numbers. How do you find out which one is the smallest? So you want to find minimum out of these m numbers. So that would be my output, right? Well, there are many ways many algorithms you can use. For example, you can do sorting, right? Give you m numbers, you have very efficient sorting algorithm. And based on this sorting, you can find which one is the minimum minimizer. Is that okay? And then you return the index of the minimizer. That will be the first stage. Find minimum from m numbers. Is that okay? Again, this thing will be very conveniently implemented on a DSP rather than analog domain. Okay? So that 3 stages would be one possible design, one possible architecture design for my receiver. This is my receiver. Is that okay? So if you are what I have gone through is the thinking logic behind an architect. So if you are an architect, your system engineer give you this equation, give you this algorithm. You need to think about how you map this equation into implementable structures. Is that okay? Now this is not the only one, this only possible design. Another possible design is like this. Let me erase this. Now, look at this metric. This is what we're trying to do, right? Okay? Now let's try to expand this metric. Quadratic expansion, right? So this will be expanded into 3 terms. Right? Okay, so now let's examine each of this term. S is the variable, right? S can take one of these m possible values. So you want to pick the overall minimum value of this metric, right? As the minimizer will be the output. So for the first term of this metric, is this relevant to your minimization? This term is not relevant, right? Because no matter what is my S, this term is a constant. Doesn't depend on S, right? So if this term doesn't depend on S, why do I need to spend resource to compute this term, which is irrelevant, right? So I could get the same minimizer by ignoring this term. Is that okay? This minimizer will be the same as this minimizer. Agree? I'm not talking about the minimum value. The value, of course, will be different, but we are not interested in the minimum value. We're interested in the minimizer. The minimizer will be the same if we exclude some irrelevant term. Okay? This is the same as if I want to find the minimizer of this. This is the same as the minimizer of this. Is that okay? Okay, so all right, so we have this. Now, we don't want to have the negative sign here. We do some normalization. This is the same as arc mass of S minus 1/2 of this. Is that okay? We flip the negative 1/2 into this. Minimum becomes maximum. Okay? Now what is this? So then we can focus on building hardware to compute these 2 relevant terms, like this. Okay? So what will be the architecture? Similarly, our input is a noisy observation waveform. So what should we do? We want to build this guy, right? What is this? This is the inner product between yt and st, right? So we can directly compute this term. Inner product is just an integration, right? Testing. This is yt and s1t. Okay? And then this is yt and s2t. yt and smt. Is that okay? That becomes my first stage. This is only computing the first term, right? I need to subtract this second term. What is this second term? Norm of S squared simply means the energy of the transmitter symbol, right? So now if all my signal set members, S1T up to S1 up to SM, they are equal energy. If the energy is the same, then this second term is also irrelevant. Then we can even ignore this second term. But in general, let's say they do not have the same energy. Then we need to correct for the bias. Then my second stage, still the first stage, I need to correct for the bias like this to account for the second term here, minus the energy divided by 2. This is also minus the energy divided by 2, minus the energy of the M hypothesis divided by 2. Is that okay? So this blue operation is to account for the second term. After this output will be the metric. So with this metric, what I need to do next is I have M numbers. This time I want to find the maximum, the maximizer. Is that okay? So again, it's the same problem. I give you M numbers. How do you return the maximizer? You do sorting, right? So this will be a different architecture, right? It's a second receiver design. Is that okay? So which receiver design 1 or design 2 have better performance? Which one has the better performance? They have the same performance, right? Because they are just two ways to implement the same algorithm. The algorithm is this thing, okay? This is the algorithm. So they will have the same performance. They may have different implementation costs. For example, this one requires M correlators. The first one only requires 2 correlators. Is that okay? So they may have different costs consideration, but they will have the same performance. Okay? So these are just examples of trying to illustrate what's the jobs of an architect like. Okay? Your input as an architect, your input is always the algorithm from the system engineer. The output of an architect is some structures like this so that you can pass individual modules to your developer for them to develop. Okay? And when they integrate, you are also the one to figure out, to do the so-called integration. Well, this is what we call integration test. I'm sure you have come across this in your undergraduate projects, right? You may assign this classmate to do A, this second classmate to do module B. When you integrate together, usually, most of the time, the integrated system will not perform as originally expected, and you have to go through debugging effort, right? So this debugging effort is a test of your system level knowledge. So usually there are different levels of bugs, right? When you integrate this thing together, the easiest bug is the error probability is 50%, okay? That basically means something is having problems, right? So it basically doesn't work at all. And then you figure out some bugs here and there, and then you fix, finally the error probability becomes, let's say 10%, okay? So it seems like it's working. But you do some benchmarking, 10% as this signal to noise ratio is still higher than the normal bit error rate. Okay? In this case, the debugging effort is more involved. You need to figure out which block, which particular module is the contributor to this abnormal error probability performance. And that requires very detailed system understanding, system level understanding. Is that okay? But anyway, later on when we talk about the later part of this, what we call rake receiver, I will give you another example. I'll give you another example of a more real-life example. Actually, that was a real case study. It's coming from a real chipset design. So when we come to that part, we'll explain using that real example, trying to explain the role of an architect once again. Okay, this is like a trivial example because the algorithm is just one line. Okay, but still, given that one line equation, you can still map into different implementation structures with different considerations and different costs. So this is what we talked about just now. This is design 1, and then there's a design 2 as well. Okay, so this is the logic behind the design 2. Okay, so anyway, so we finished the first goal. How do we do optimal demodulation? How do we design the receiver? Okay. The second goal we are going to talk about is, okay, given we use this minimum distance demodulation, which is the best receiver, by the way, what would be the error probability and what would be the error mechanism? Okay. So, and I guess we can take a 15 minutes break, and then we come back to talk about the second question, the error mechanism. Okay.
突然有一天跟我讲说猜出来了。 这
Okay, let's resume. All right, so now after the break, we try to go over the second goal, which is try to understand the error mechanism. All right, so it's a bit chaotic on the notes, but let me elaborate on the whiteboard. Okay, so we understand now the best receiver we are trying to do is the minimum distance demodulation. That means the output of the receiver will be picked from the hypothesis that is closest to the current observation, because that is the best explanation for the observation. Is that okay? So now with this receiver, let's look at under what circumstances will we make a mistake. Okay, so we consider to help you to understand, we consider two extreme cases. Let's say I have a quaternary modulator, and these are the four members in my signal set. Okay, so that means without noise, your receive point will be in one of these 4 points. Okay, so this is the signal space. Okay, so now we always use the minimum distance demodulation, right? So let me consider a few scenarios. So let's say in this first scenario, the noise power is pretty low, or the signal to noise ratio is very high. Okay, so what does that mean? That means if I transmit S1, my observation will have high probability of lying within a certain noise cloud of a small size, right? So let's say this is my noise cloud. So if I transmit S1, I may have an observation here. I may have an observation here. Okay? So if I transmit S1 1,000 times, 10,000 times, all the observation will lie somewhere within this cloud, right? As we have explained the mechanism. Okay? And let's assume this is a small noise scenario. So the noise cloud, the size of the noise cloud is pretty small. Okay? So now, let's say I transmit S1. And let's say this is my current observation. Okay? We will always be using minimum distance demodulation. Now in this case, what will be the output of your receiver? S1, right? Because obviously, in this case, S1 will be the best explanation for the observation compared to S2, S3, S4, right? So, and then, since we assume you transmit S1, and then your output is S1, so in this case, you see that you don't make a mistake, right? Okay? So next time, if your observation is here, likewise, using minimum distance demodulation, your output will be S1, right? Again, you don't make mistake. So you can see that in this case of small noise situation, so given, likewise, if you assume you transmit S2, then most likely the observation will fall within this noise cloud. And in this case, you also won't make mistake. Is that okay? Now, so that is the small noise scenario. So now let's look at another extreme. So this is again the received signal space. It's S1, S2, S3, and S4. Okay, the same signal set members. But in this case, let's assume we have large noise power. Okay, so that means if I transmit S1, very likely with high probability, my observation will lie within a certain noise cloud center about S1, right? But now let's assume the noise power is large. So the size of the noise cloud is bigger. So let's say this is my noise cloud about S1. Is that okay? Now then let's look at the situation. If I assume the transmitter point is S1, then this time my observation may be here. If my observation is here, I'm always using minimum distance demodulation. So my output would also be S1, right? Because this is the best explanation for this current observation, right? Now next time, I may be here, right? And I still will pick S1 as my output because that is still the best explanation for the current observation, right? Now, however, the noise cloud is very big, so we can draw an equivalent noise cloud about S2. But what if assume I transmit S1, but what if my observation now is here? Then what will be your output? Your output will be S2, right? Because S2 seems to be a better explanation than S1 for the current observation, right? But then you assume S1 was transmitted, and this time your output is S2. So therefore, you make a mistake, right? Now, so can you visualize the error mechanism? Error will occur whenever you are in the overlapping region between the noise cloud. Can you see that? Likewise, you can extend the analysis to consider noise cloud about S3 and noise cloud about S4. So all the overlapping area between the noise cloud would be the dangerous area. When your observation lies within this overlapping area, you will make a mistake. Is that okay? So, therefore, geometrically, the error probability is related to the overlapping area between noise cloud. Can you see that? We all agree with this statement, right? Because we visualize when error or when the mistakes will happen. Is when the observation lie within this overlapping area in the signal space. Okay? So how likely you make a mistake, the so-called error probability, of course, depends on how big is your overlapping area. The bigger the overlapping area, the higher the probability that you will land on this, this overlapping area. Is that okay? Now, so this is a very important intuition. Now, so how can you reduce the error probability? To reduce the error probability geometrically, you need to reduce the overlapping area, right? So that depends on what you can do, right? Obviously, one choice is if I can shrink the size of the noise cloud, then the overlapping area is reduced, right? Shrink the noise cloud size means I reduce the noise power, right? But as I said, usually you have no control on the channel. You cannot change the noise power in the channel, okay? That's something you don't have the freedom to do it. So for a given size of a noise cloud, what else can you do to reduce the overlapping area? The center is something you can design, right? If you can pull the noise cloud further away, then you can reduce the overlapping area and therefore reduce the error probability. Can you see that? Okay, but what exactly do we mean by pulling the center, moving the center away? We have to increase the transmit energy. Can you see that? Because the energy of the signal is equal to the distance square from the origin, right? If I physically pull this noise cloud away, of course the overlapping area will be reduced. Error probability will be reduced, but my cost is I need to increase my transmit power. Is that okay? So this explains this trade-off mechanism. If I can increase my transmission power, that means geometrically, I can put this noise cloud further apart, and then geometrically, I will reduce the overlapping area, and therefore reduce the error probability. Is that okay? So that is another obvious trade-off. Now we can understand the error by this geometric visualization of the error. We should be able to understand this trade-off easily, I hope. Okay? So therefore, as we point out here, so the error probability is related to the overlapping area. The way to reduce the error probability is to reduce the overlapping area. Okay? But then there are different means of reducing the overlapping area, and they will have different costs. Okay? So we are going to go through this. Now, for a given size of a noise cloud, let's say if I only have binary modulation, if I have two-dimensional space, and then let's say these are my only two members in my signal set, okay? Then in this case, the overlapping area depends on what? For the fixed size of the noise cloud, the overlapping area depends on the distance between these two centers, right? Okay? So if I want to reduce the overlapping area or reduce the error probability, I need to do something to increase the separation of the centers. Is that okay? Now, if I have 3 points in my signal constellation, then we are talking about multiple overlapping areas, right? We are talking about the overlapping areas between these two noise clouds, these two noise clouds, and these two noise clouds, right? So when we say, if just or do it this way, if I have 4 points, and then this is S4. So imagine you have a noise cloud center about each of these points. Okay, I don't want to draw the noise cloud here. Now, if you try to spend some extra energy, and then you just move this point, this noise cloud away, will this help? If you just spend all the energy budget to move this noise cloud center away like this, then because of the increase the distance of this S2, you need higher energy, right? But if you do it this way, you spend all the energy to move this single noise canal away like this, is it going to help to reduce your error probability? It is not going to help because, yes, you move this noise canal away, but you also have the other noise canal. Then the bottleneck of the error probability will be between S1 and S3, S3 and S4. Is that okay? So by this argument, the best way to put the 4 points, to design the 4 points in your signal set is not to have any bottleneck. Is that okay? So therefore, a good design for the 4 points will never be something like this. It will never be like this. Okay? Because with this, you will see clearly you have bottleneck in your error probability. If you have bottleneck, that means you can pull this closer and then use the extra power. Now, power or energy means distance square. Okay? If you have a design like this, you may have a better design by moving this slightly closer. So you have some slack energy budget. And you use that slack energy budget to move the other points slightly further away to help the bottleneck. You understand what I mean? Okay? So by this argument, the best design would be symmetric design, where you don't see any bottleneck. Is that okay? Because whenever you have a bottleneck, you can always use this trick to move this point slightly in closer, so that you have some slack energy budget, and you use that slack energy budget to spread over the other bottleneck, and that will have a better performance than this one. Is that okay? All right. So when you have more than 2 points, more than binary modulation, then the error probability is determined by the bottleneck, the worst case overlapping areas. Put it this way: the worst case overlapping area which depends on the worst case separation of constellation points. So for 4 points like this, the worst case separation is not between this one and this one, not between this one and this one, not between this one and this one, but between these two and this two. Is that okay? So you can argue most of the errors will not be coming from S2 into something. Most of the error will be, for example, S1 into S3 or S3 into S4. Is that okay? So in other words, so what's the worst case separation of the constellation points? In other words, is related to the minimum of Si, Sj. Si and Sj are any two constellation points. Okay? You compare the distance separation between any two constellation points, and the worst case separation will be your error bottleneck. Is that okay? So if you want to spend some energy to improve the error probability, the energy should be spent to help the bottleneck. The energy should not be spent on something which is not the bottleneck. This is just to say, if you have a configuration like this, and suddenly I give you some extra energy budget, the extra energy should not be spent to move this point further away, because it's not going to help. The extra energy should be spent to move, for example, this point further away, this point further away, this point further away. Is that okay? So always address the bottleneck. And the bottleneck in an Emery modulation is given by the worst case separation between any two noise canal centers. Any extra energy should be spent to address the bottleneck. Okay? So keep this in mind. Now, so with this is the why part, why we want to spend some time to talk about geometric domain representation. It looks abstract. But once we look at this whole thing, the receiving or detection process from a geometric domain angle, the detection problem and the error mechanism is purely a geometric problem. Okay? We can understand the error mechanism from purely a geometric concept and geometric intuition. Once we have this geometric intuition, we can also think of solutions or think of ways to improve the error probability, again, from a geometric domain angle. I will give you more examples later. And this is, I hope, much easier to understand compared to if you have double E background before in your undergraduate. I think most of the time you will be, the approach, you learn this digital communication error analysis will be the algebraic approach, where you've gone through some tedious algebraic analysis, and the error probability is a Q function of something, okay? But in fact, to understand this intuition, you don't need that kind of complicated equation. Just map this problem into a geometric domain angle would enable you to have lots of visualization. This is because I guess most human beings will be good at visualizing a geometric problem than visualizing an algebraic problem, okay? Now I'll give you more examples in a minute. So, all right. Now, before I explain this four trade-off mechanism, which I have explained two already, okay? Let me give you some examples so that you can you get some hands-on example on how we apply this geometric domain picture into explaining or comparing which of these modulation design is better than the others. Okay, so let's look at a few examples. Now let's look at, okay. Let's say we start with binary modulators. So let's say I have one binary modulator called ASK, BASK, amplitude shift keying. And the signal set for this amplitude shift keying, or somebody call this on-off keying, is simply, remember, it's a binary modulator. So this is, we just need to fill up this signal set with two members. Okay, so for BASK, the two members are like this. It's a bunch of sinusoidal waveform. Okay, so this is A cosine omega ct. S2t is just 0. So these are two different waveforms, right? So this can be a legitimate binary modulator. And this modulator is of some importance in the application, so it's worth a name. This name is called amplitude shift keying, okay? Because it's like you are using the amplitude of the sinusoidal waveform to signal 1 and 0. This is 1, this is 0. Is that okay? So this is one design. Now another famous design is called BPSK, binary phase shift keying. So using our black box model is nothing but just another design, okay? And this second design is like this. My S1t is a sinusoidal burst given by A cosine omega ct. And my S2t, my second member, is 180-degree phase shift. So it becomes something like this. A cosine omega ct plus pi. These, again, are two different waveforms, right? So it forms a legitimate binary modulator. Is that okay? So we can have arbitrary, you can easily dream up your own binary modulator, okay? Now let's try to look at this too. Now, although these two function as a binary modulator, they have the same bit rate equation, same bandwidth, blah, blah, blah. But which one has a smaller, which one is more energy efficient, put it this way? Energy efficient means using the same energy, which one can achieve a smaller error probability? Or if both have to achieve the same error probability, which one requires less transmit power? You understand what we mean by better, right? So which one is more energy efficient? ASK, right? Now, let's do an opinion poll before going through the analysis. How many of you will, I'm asking which one will be more energy efficient? Which one will save more energy to achieve the same error probability, okay? Anyone vote for ASK, raise your hand. A few hands. Don't be shy, okay? You just voice out what you believe. Now, there are reasons that you believe in this, right? Thank you. Because here in ASK, what does that mean? That means 50% of the time you turn off your transmitter, right? So turning off your transmitter is a very good way to save energy, right? whereas in this case, 100% of the time you turn on your transmitter. So you would probably guess this one is more energy efficient than this one, right? Correct? Now let's try. Now, again, looking at this comparison using time domain waveform is, we can still take the algebraic approach that some of you may have learned before to go through the analysis. But now, since we learned the geometric approach, let's try to do the comparison on the geometric domain, okay? Now to do this, because now the way I specify my signal set is using time domain waveforms, right? So the first thing we need to do is to convert this into geometric domain first, right? Before we can apply the geometric domain framework. Now, of course, we have talked about the two steps last time, right? If you like, you can go through the systematic procedure. Step 1, you can use your GSO procedure to find the basis. And then once you have the basis, you can find the coordinate using inner product projection, right? Now, but for this simple case, let's say we don't follow this standard procedure. Let's say, because we are talking about two signals only, two members only. So let's say a two-dimensional space would be big enough to represent these two members, right? In the worst case. So let's say we have a two-dimensional space, I and Q. For this case, so we are not worrying about the detailed coordinate, but we want to understand what's the constraint, the constellation constraint or constellation properties of the 2 points associated with BASK. Now, without going through the serious derivation of the basis and derivation of the coordinates, what can you say about the 2 points for ASK? There are 2 points, right? For these two members. What can you say about the coordinate of these 2 points? These 2 points cannot be arbitrary on the space. These 2 points have to satisfy some constraint. One point must be at the origin, right? Why? How do I know this point must be at the origin? Because you look at this S2. S2 is 0, right? That means what? That means S2 has 0 energy, right? And remember, what is energy in the geometric domain? Distance of the point from the origin square means energy, right? So now with this time domain design, I know this is the distance of the second point to the origin is 0. And there is only one point that has 0 norm. That point must be at the origin, no matter what is your basis. Is that okay? So for this BASK constellation, I don't know where is the first point. First point maybe depends on the specific design of the basis, right? First point can be arbitrary, but the second point must be at the origin. Is that okay? So that is the structure of the 2 points in ASK design. Okay? Similarly, for the BPSK, what can we say about the 2 points in the two-dimensional signal space? Again, without going through very serious derivation. Just from the time domain observation, what kind of structural constraint or structural properties we can infer for the 2 points? Say if one point is here, where would be the second point? First of all, I hear two things. One is symmetric, the other is same distance, right? Now, exactly. You look at these two time domain waveform, what can you say? First of all, they have equal energy, right? Equal energy means distance is the same, right? So if one point is here, the other point cannot be anywhere, right? The other point must be, at least from this, it implies the second point must be on this circumference, right? But what other information help us to locate where is the other point? You look at this waveform. It's not just equal energy, right? What can we say? Cosine omega ct plus pi equals to what? Equals to negative cosine omega ct, right? Right? So that means S1t equals to negative of S2t. Can we see that? So if we convert that to vectors, that means S1 is equal to negative of S2. Can we see that? So this gives you a constraint. If S1 is here, S2 can only be here, equidistance, and directly opposite. Is that okay? Okay, so without going through this step 1 and step 2, for these two simple cases, we can say the two constellation points for ASK would be like this, for BPSK would be like this. Is that okay? So now, let's do the comparison based on the geometric domain picture, right? I'm asking which one is more energy efficient, right? That means which one will consume less energy to achieve the same error probability, right? Now, as we have just explained, to achieve the same error probability, that means the noise cloud separation must be the same in both cases, right? Okay? So if, let's say, this is 1 unit here and 1 unit here, so that the noise cloud center separation is separated by 2 units, right? In order for this one to achieve the same error probability as that, that means this 2 separation must be 2 units as well. Can we see that? When we set up these 2 constellations this way, the 2 design will have the same error probability. Agree? Because once again, what is error probability? Error probability is determined by the overlapping area between the 2 noise clouds. The size of the noise cloud is determined by noise power, which we cannot change. So the remaining factors that affect the overlapping area is the separation of the center of the noise cloud. By this setting, the separation of the center of the 2 noise clouds is equalized to be 2 units in both cases. So therefore, they will have the same overlapping area, and therefore, they will have the same error probability. Agree? Okay. So now our remaining task is to figure out which one consumes more energy. Okay. For this one, what's the average simple energy for BPSK? We have 50% of the chance, half of the chance we transmit S1, right? When we transmit S1, what's the energy? 1 unit here, right? 1 square. Is that okay? Distance to the origin square gives you the energy for S1, right? Another half of the chance we transmit S2. When we transmit S2, what's the energy? Also 1 square, right? So what's the average? 1 unit, right? Let's try to do this for here, for the BASK. Again, 50% of the chance when we transmit S1. When we transmit S1, what's the energy? 2 square, right? And then when we transmit S2, 0 square. So what's the average? Average is 2 units. So what is the answer? Which one is more effective? This one is more effective, right? Despite in the ASK design, if you just look at time domain waveform, you may have the wrong intuition that I turn off my transmitter 50% of the time, so I must be more energy efficient. In fact, the other 50% of the time when you turn on, you have to turn on much higher power, so that on average, you lose out. Is that okay? In fact, from this comparison, this is just a pure geometric problem, right? We can not only figure out which one is better, we can even compute how much better. For example, usually the standard way to plot the performance error probability is this is bit error rate. This is ES over N naught, the transmit power in dB. Okay. The normalized simple energy to noise density ratio. You think of that as the normalized signal to noise ratio. Okay. So first of all, the curve will be decreasing or increasing. The curve will be like this or like this. Decreasing. Why? Because as we increase the simple energy, geometrically, we are moving this point away, right? So moving this point away can only reduce the overlapping area. So we expect the curve to be like this. Is that okay? Now we have 2 designs, so we have 2 curves. One would be BASK, one is BPSK. Which one is BPSK? This one or this one? Let me label it. This is A, this is B. Which curve corresponds to BASK? A or B? BASK. This should be A, right? Because how do we read this? Well, what we have done is to achieve the same error probability, one design requires less symbol energy than the others, right? So which one require less? BPSK require less, so this would be BPSK, right? And then the other one would be BASK, amplitude shift keying here, right? How much better? 2 times. BASK require 2 times the average symbol energy compared to BPSK. 2 times in log scale means 3 dB. So we know this gap is 3 dB. Is that okay? We can even quantify the gap. Is that okay? So this is the first example. I guess this is fine, right? Let's look at another example. Okay, let me consider another example. Well, let me redesign another one. So let's say, do I have any other thing? No, okay. Let's say let's consider another design, BFSK, frequency shift keying. Now for those who have studied digital modulation before, BASK is called the digital version of AM, okay? BPSK is called the digital version of phase modulation, because obviously you're using the phase difference to signal between 0 and 1, whereas the ASK is using the amplitude to signal 0 and 1. So that's why the names come after this feature, this time domain feature. And then the third one is BFSK, is the digital version of FM. That means you expect it's using different frequencies to signal between 1 and 0. But we can still use the black box model to embrace this different design. For BFSK, it's just another 2 different signal members. But the 2 signal members have a special structure. It's a bunch of sinusoidal cosine omega 1t. And then S2t is A cosine omega 2t. It's faster frequencies. Okay, where this omega 2 minus omega 1 has to be 1 over Ts. This constraint is to make sure that as you change between 1 and 0, you have a continuous phase. Okay, you don't want to have phase discontinuity because that will generate high order spectrum, whatever. Okay, so you have this constraint in the signal set design. Well, using our model, we don't need to worry about why we have this constraint. We just have a special design that these are the 2 different members in my signal set. I set it this way, and this design have a name called BFSK. Is that okay? Now, how about this comparison? Which one is more energy efficient, BFSK or BPSK? Well, we use, again, so this is why specifying your signal set using time domain waveform is not preferred. Because if you want to do a comparison, you always need to go through the trouble to convert the time domain representation to geometric domain representation. If that's the case, why don't you specify your signal set members directly on the constellation space? So that's why the geometric domains, the so-called constellation diagram, is a more common way to specify the signal set of your modulator in most of the textbook. Okay, but now for the sake of this discussion, let's say I use the time domain specification for my other binary modulator, and this one deserves a name called BFSK. Okay, so again, which one is more energy efficient? If you look at the waveform, time domain waveform, again, it's very difficult for you to draw any useful intuition. Again, we use the same approach to consider this in the geometric domain. Let's say, again, we have 2-dimensional signal space. We don't worry about the detailed coordinates. We still focus on just extracting the first order constraints between the constellation points. Okay? Now for this BFSK, what can we say about the 2 points? Now if one point is arbitrary, let's say this is my first point, what can we say about the second point? Can the second point be anywhere? That depends on the feature you can extract from this time domain waveform, right? What can you say about the second point? Now, first of all, you will see that these 2 members, they have the same energy, right? They are just sinusoidal bursts with different frequencies, so the average energy is the same. Same energy means at least you will have this, right? So if one point is here, then the second point must be on the circumference of this unit circle, right? Of this circle. It may not be unit circle. Okay? But what else can you say? There is one subtle properties from the time domain waveform that helps you to locate where is S2. S2 cannot be arbitrary on any point of the circumference due to that second constraint. Anyone remember BFSK if you study this in the undergraduate? There's one important properties of BFSK. The properties is, if you look at the inner product, the inner product of these two particular members happens to be 0. Now, why this is 0? You can work out the algebra. So the definition of inner product is like this, right? Integration of S1T and S2T multiplied together, right? S1T is A cosine omega 1. So you have A squared outside. This is cosine omega 1T, cosine omega 2T, right? How do you integrate this? High school calculus, right? Remember in high school you have this product to sum formula, right? Cosine A, cosine B will be expressed in terms of cosine A minus B and plus cosine A plus B, right? Cosine A minus B will be the difference between these two frequencies. By this constraint, this difference will be integral multiple of this simple frequency, right? So you integrate over one period. So that cosine A minus B will be 0. Cosine A plus B, similarly, you are integrating over multiple periods of a sinusoidal wave. So the average or DC level will be 0. So because of that, this turns out to be 0. Is that okay? You can try this offline using just simple integration. Okay? So just trust me for now that if you take the inner product between these two members, they will be 0. So what does that mean geometrically? That means S1 is orthogonal to S2. Is that okay? So S1 is orthogonal to S2. That means if I set S1 to be here, then where should be S2? Either here or here, right? By symmetry, without loss of generality, I just assume S2 is here. Is that okay? So that would be the 2 points, the configuration of the 2 points associated with BFSK. Okay? BPSK is the same as before. One point is directly opposite of the others, equidistance. Okay, now, so we're ready to do a comparison. For B, once again, we want to set up the two systems so that they achieve the same error probability, right? For BPSK, I set it to 1 unit here, 1 unit here. So the 2 points are separated by 2 units. Can you see that? Now, for this design BFSK to have the same error probability, what do we need to set? This distance needs to be 2 units, right? If we set this distance to be 2 units, then the two design will have the same error probability. Why? Because you imagine you overlay the noise cloud onto these 2 points, these two design will have the same overlapping area between this imaginary noise cloud. Okay? Now then, the remaining steps is to figure out which one consumes less energy. So we know this one, the average simple energy for BPSK is 1 unit, right? What about this one? Well, to figure out the energy, we need to figure out this psi first. This is an isosceles triangle, right? These two sides is equal. The hypotenuse is 2. Then what about this side? Square root 2, right? So this is a simple geometric problem. Is that okay? So what is the simple average simple energy of BFSK? Half of the time you transmit S1. If you transmit S1, what's the energy? This length square, right? So square root 2 square plus half of the chance you transmit S2. When you transmit S2, what's the energy? This length square, right? So square root 2 square. At the end, what is the result? 2 units, right? So which one is more energy efficient? Still this one. How much more energy efficient? 3 dB, once again. In other words, this one is the same as BASK in terms of the error performance. Okay? If you think about the error probability curve, y-axis is probability of error, x-axis is ES over N naught in dB. This curve, BFSK and BASK will have the same curve. And they are 3 dB worse than the BPSK curve. Is that okay? So you see that this is very powerful. The comparison or the error analysis is literally reduced to a geometric problem. Is that okay? All right, let me give you, I still have time hopefully to cover this. Let me give you a more challenging example. Okay? Let's say now I still use BPSK as a baseline. And then now let's say now I dream up my own design. Let's say my first member is this design, this waveform. And my second member is this design. These are two different waveforms, right? So if legitimate functionally serve as another binary modulator. But this dream up design doesn't worth a name, right? So therefore it's just another design. Let's call this design B. Okay, now for easier discussion, let's assume we design the waveform such that the energy is the same. Okay, so now I ask you, which one is more efficient? To answer this again, if you take the geometric approach, you need to figure out where are these 2 points first. So what can you say about the 2 points? Similarly, if I don't know, if 1 point is here, what can you say about the second point? Of course, the fact that they have equal energy means that norm, the 2 points are equidistant from the origin, right? So the other point must be somewhere on this circumference, right? Beside that, what else can you say? Where would can the second point be anywhere? Where could be the second point with my dream up design? From the waveform, from the time domain, there is one additional constraint or one additional information. What is that? This is a generalization of the BFSK. In the BFS case, why can we locate the second point? We consider what? We consider the inner product, right? Turns out the inner product is 0, so we conclude that for BFSK, the 2 points are orthogonal, right? What about this? We can consider the inner product. This inner product, what can you say about the inner product? Is it 0? It's not 0, right? Because this inner product is defined to be this integration, right? If you look at this integration, it cannot be 0. But what can you say about this inner product? It's not 0, but what can you say? Can it be arbitrary? It cannot be arbitrary. It's non-negative, right? It's positive, right? Why? How do we know it's positive? But you just do the integration. Think about S1t multiplied in S2t, right? All these values are this positive value is multiplied into positive value. At all time, it's positive times positive. So this integrand is positive over the entire period, right? Integration is just a summation. You sum up a bunch of positive numbers. The result would only be positive, right? Is that okay? So what does that mean geometrically? This is how we define angle between vectors, right? How do we define angle between vectors? If I have two vectors, x and y, This angle is theta. How do we define angle? High school vector algebra. Cosine theta is defined to be the inner product normalized by the length. Right? That's how we define angle. So now, the fact that this inner product is positive, what does that tell us? The denominator must be positive, right? It's the length. The numerator now for this design is positive as well. So that means cosine theta is positive. Cosine theta positive, what does that mean? That means this theta will be in the first quadrant or the fourth quadrant, right? So that means if S1 is here, then S2 can only be here or here, right? By symmetry, let's assume it's in the first quadrant. So if S1 is here, S2 could be here. Is that okay? So with this configuration, which one is more energy efficient? Of course, still this design. Why? Now this time we can argue the other way. Let's try to equalize the energy and see which one have a lower error probability. It will be easier this way. So it's a unit circle, right? So for this one to achieve the same energy, this is also a unit circle, 1 unit here, right? Then the resulting error probability is determined by what? Overlapping area, right, as always. And overlapping area depends on what? Depends on the separation of the centers of the two noise clouds. That is the separation of these 2 points, right? So the question becomes a geometric problem. I'm asking you which one is more energy efficient. This is the same as asking you in this two setup, which case will have a higher separation between the 2 points. Of course this one, right? This one has a separation of 2 units. And this one, I don't know what's the separation, but for sure, this separation must be smaller than 2, right? This is a simple geometry. If you want to work out the separation, you can do cosine rule, right? So you have a cosine rule to work out what's the distance here. And of course, this distance must be less than 2. Is that okay? For this reason, this one will have a higher error probability compared to BPSK under the same energy. Is that okay? If you like, we can even figure out how much worse, right, by computing this distance. Is that okay? So this is another example of the powerfulness of this geometric approach. So once you have this kind of geometric insight, the insight is very simple. Error probability is just determined by the overlapping area between this imaginary noise cloud. Once you have this intuition, then you can do a lot of analysis, okay, based on this simple geometric intuition. Okay, and from these 3 examples, you can also deduce that this is actually the best case, the best possible case to put 2 points on a constellation on the 2-dimensional space, right? Because the cost, you pay 1 unit of energy cost to separate these 2 points, right? Now, so of course you can, let's say 1 point is fixed to be here, the other point you have the freedom to move around, right? When you put the second point anywhere on the circumference, the cost is the same, right? But which position will give you the maximum benefit? Of course, this is the position, because benefit is represented by the separation, right? So for the same cost, if you are able to decide where is the second point on this circle, this point would give you the maximum benefit or the lowest error probability. Is that okay? So, and again, this conclusion is coming from simple geometric argument. And that's why this is also called antipodal design. So what matters is not the specific waveform. For example, if I have my design like this, so that S2T is negative of S1T, then this design will have the same performance as this design, although they have different waveform. But the geometric structure of the 2 points will be the same. Can you see that? So at the end, what matters is not the specific waveform in your signal set members. What matters is the geometric configuration of the 2 points in your signal set in the constellation diagram. Is that okay? So that's why I said earlier on, although it's a matter of your personal style to describe your signal set using time domain or geometric domain, but based on this benefit, it's much more convenient to specify at the beginning your signal set directly using constellation diagram. If you specify this using constellation diagram, it saves us the trouble to convert from time domain to geometric domain. We can just look at this geometric domain constellation points configuration and directly compute or do the comparison. Is that okay? So that's why in most of the textbook or data sheet, you don't come across very often the specification using time domain. Most of the specification of the signal set behind a modulator is specified using constellation diagram directly. Is that okay? All right, so that is a long answer to the why part of the geometric domain representation. Okay? With geometric domain representation, we can transform the problem into a geometric problem, and then so that average person can develop intuition or visualization much easier with geometric problem than algebraic problems. Okay. Now I still have a few more examples, but I don't have time to go over this now, so I will continue next week. Okay. So let me stop.